Hello, all. Good to see you.
Hello, Prof. Good morning.
Um, so I'm thankful for all of you that did testimonials. I'll be going, I think, in 2 weeks to that conference in Miami for Africando, and I'm going to try and see what kind of money I can drum up for internships and fellowships and scholarships. So I'm really glad that you guys did those testimonials. So thank you very, very much. That's going to be very helpful. With that said, I want to get to, since we're getting close to the end of the semester, I want to get to kind of like the end of the mid-semester. I want to get to one of our presentations and discussions. So up until now, we've been talking a lot about what's known about the climate record. We've talked about the physics behind how we have temperature on the planet and how it responds to radiative forcing, how it responds to the sun, how the addition of an atmosphere affects what temperatures we see and therefore what climates we see. And so I want to kind of continue on that discussion. Go ahead and share my screen. Share sound, there we go. So all of this is based on chapter 7. So if you've got the book, please read along. If somebody has a PDF of the book, please send it along to me so I have a copy of it, because I've got a paper copy, but sometimes it's nice to get some of those figures. In any case, so what we know from the IPCC, it says that the evidence for climate change is unequivocal, meaning that there's no question that the climate is changing, the temperature is increasing. And we know that from this global temperature anomaly, which we've measured to be about 1.1 degrees Celsius since the 1860s, using a reference period between 1950 and 1980. And so we know that we're getting this warming of 1.1 degrees that's occurred over about the last 150 years. That's a relatively short period of time. If we look at what we know of from paleoproxies about the temperature of the Earth long ago, so this is looking about 70 million years back, we know that it used to be much warmer and that it has slowly over tens of millions of years, the temperature has decreased. So we know that the climate has changed significantly over time, to the point where it had actually reached a peak of possibly 20 degrees Celsius over today's temperatures. When we narrow that down and we look at a later slice of this, so these are temperature anomalies from about 400,000 years ago, we can see that our climate started to cycle. Let me go ahead and get rid of that background noise. Okay. That our temperature started to cycle. We started seeing these ice age versus interglacial cycles about every 100,000 years. And that brings us kind of up to the present day over here. So if you look at these cyclical peaks, we should be on our way on a downward peak. And note that this is about a 1 degree Celsius change per 1,600 years. Okay, so when we talk about this climate variability over the cyclical ice ages, we're talking about a Celsius degree change every 1,600 years. If we expand that out in the last 10,000 years, at the end of the last ice age was about 10,000 years ago. And then we see that we're in this interglacial period where the temperatures are warm. and then they started to decrease, and we hit what we call the Little Ice Age in medieval times. And then all of a sudden, our temperature is starting to spike. And so the topic of today's lecture is really what's causing it. How can we attribute this climate change? Okay. We've talked about why CO2 would be expected to cause climate change, right? The fact that we get black body radiation from the planet, it's in the infrared, CO2 absorbs in the infrared. We've looked at theoretically how having a layer of CO2 would affect the surface temperatures and would increase the surface temperatures through a greenhouse effect. But have we really shown that that is what's causing climate change? Right? We've looked at the theoretical part. We've talked about what one would expect. We're seeing changes in our climate. But is it really that the only factor? And is that the thing that really is the attribution for climate change? Now, one of the things that I think it's important to mention, we like to talk about logical fallacies a lot in this course. We have to remember that correlation isn't causation. Just because two things are correlated at the same time doesn't mean one causes the other. So if every time there is an eclipse, I start playing the drums to bring the sun back every single time, and the sun always comes back after the eclipse, that doesn't mean that my drumming actually caused the sun to come back. It's just a correlation. It doesn't mean there has to be causation. I mean, we have seen that the increase of CO2 does seem to track very closely with the temperature. But again, that doesn't mean that one caused the other. Okay, it might be the reverse. Maybe the change in temperature caused the CO2 rise, right? So we have to look to see, when we want to find what's responsible for our present day climate change, we have to think about what are all the different possible factors. And if you go onto the internet, you're going to find loads of different counter theories to what's causing climate change, because there are folks out there who have a lot of monetary interest in attributing climate change to anything else other than the burning of fossil fuels, because that would mean we'd have to cut down on fossil fuels and some people wouldn't make huge amounts of money. So there's a lot of folks out there that want to propagate a lot of these other possible attributions. So let's go through them a couple at a time to see, what makes sense. What are some of these other factors? And so here's a list of them, which are the most common ones you'll find. One is continental drift. Another is changes in the sun. Others are orbital variability or an unforced variability. And lastly, the only really other big one is greenhouse gases. And so we'll just talk about all of those in terms of attribution for what's really causing climate change. So the first one is continental drift, okay? And so what I'm going to show you here is a little video that's kind of showing continental drift over the last 200 million years. Hold on a second. Why is it not? Let's see. Hold on. Let's see if I do it this way. Oh, give me a second here. Where's my little videos not going? Give it just a second here. Let's see. It says I should be able to play it. It takes a second to load. Hold on a second. Just a moment here. My little video doesn't seem to want to play. Okay, hold on a second here. Give me a moment. So while I'm looking for this, this is the one we want to see. So this is showing the map that we have right now. So I'll go ahead and replay that. We're familiar with about 200 million years ago, nearly all of the continents were conglomerated together in one big supercontinent that we like to call Pangea. And that was 200 million years ago. And over the course of time, with tectonic shifts, these continents have begun to drift apart. And you can see here how they're drifting apart about 150 million years ago. So this is well into the time of the dinosaurs while they were in part of their peak. Remember, they lasted till about 62 million years ago before they went extinct. So the continents started to break apart, and we call one of these supercontinents Laurasia and the other supercontinent Gondwanaland. This is what it would have looked like 100 million years ago. So 100 million years ago is well before humans even existed. Okay. This is about 50 million years ago. We still don't have humanity has been around for maybe the last million years. And that's the progenitors for Homo sapiens. Really, it's been a lot less, maybe 100,000 for Homo sapiens sapiens. And then this is what it looks like in the present day. This is kind of what it's looked like for the last 100,000 years since humanity's been around. And this is probably what it's going to look like about 50 million years into the future. So continents move very slow, on the order of centimeters per year, just one or two, not a lot. Okay. Now, would this affect climate? Well, yeah, one could argue it would affect climate because the locations of the land really determine where ice forms, right? Ice will form on top of the land. That's where the snow accumulates. Since land is where you're going to get a lot of heat absorption from the sun, if it's not white, if it's green or brown or black, then you're going to get a lot of absorption of the sun's rays and less reflection. If you get ice, however, ice is white, so it's going to reflect and you'll increase the albedo. And we know if you increase the albedo, you would expect, what would you expect? If you increase the albedo, would the climate get warmer or colder? If you increase the albedo?
It will get warmer.
So walk me through that logic. What is the albedo again?
The constant is 0.3.
Right.
So when increasing albedo, unless I'm not thinking of it in correct sense.
Let's go back to our favorite little equation over here, right? So the albedo is listed here. And so here's the solar constant, right? We're multiplying this by 1 minus the albedo. So if the albedo is getting larger, we're subtracting a larger number from 1. And so this upper term is getting smaller, right? What's our definition of the albedo? What does it mean?
The shortest way I understood it is like basically the reflect. How do you call this? The ability of surfaces to like reflect light in terms of heat or energy from the sun.
Right. And so if you have a higher albedo, you're reflecting more light, right? Back out into space because the light that you're reflecting is still in the visible spectrum. And so it wouldn't be absorbed by any greenhouse gases. It would just continue back out in space. So if you're reflecting more light from the planet, what would you expect to happen with its climate? Would it get warmer or colder? You're taking
Cooler.
less energy in, so you'd actually expect it to get cooler, right? So as these continents move, you know, when they're collected, the more ice that they have on them, the larger albedo we would expect. Typically, we'd see that ice forming when these continents are closer to the poles. And so we would expect that continental drift should affect our climate in one way or another, depending on its albedo, okay, and how it changes our albedo. But the problem with using continental drift to attribute current day climate change is continental drift happens over hundreds of millions of years, right? So we saw, Pangea about 200 million years ago, and that's a long, long, long time. It can't really explain the sudden move, the sudden cooling or heating that we're seeing right now. So let me go back to our current temperature. Let's see where, if we look at what we just said about how fast temperature is changing, we're talking about a 1 degree temperature change in only 150 years. That's really not going to explain why in the world, or how in the world, continental drift is going to be responsible for that, because in 150 years, continents are only moving maybe a few hundred centimeters. So continental drift is really too slow to attribute to our sudden change in global temperatures. So we can kind of mark that off the list, rule that out. So next thing we can look at, what people often attribute when you look out on the web, are changes in the sun, okay? We know that if we look at our favorite equation, which tells us the temperature on the surface of the planet, given a number of atmospheres, and this comes from the Stefan Boltzmann equation, that the solar constant, plays a really, really important role. The larger the solar constant, the more energy coming onto the planet, given the same albedo. And so you would expect a larger solar constant to increase the temperature. And if the solar constant decreases, you would expect the surface temperature goes down. Okay. And since the 1970s, we have very accurate measurements of the solar constant via satellites. And so here's some of the data on that. This is published data, and the constant has been remarkably constant between, somewhere between the range of 1360.5 to 1362. And it really has, it goes along with this well-documented 11-year solar cycle that's been published a lot. So we know that there's this solar cycle to the sun, right? And this is about every 11 years. Well, we know that the global warming that we've seen has happened over the last 150 years, right? Since the 1860s. And so if these sun cycles were a part of this, you would expect it to go up and then go back down and go up and go back down. What we really need to see is a signal that's steadily increasing over time. And so that makes it really hard to kind of explain our current increase in temperatures due to these changes in the sun. So yes, the sun does change. Yes, there is a cycle to it. It's only an 11-year solar cycle. And we really need, in order to explain our data, a sustained increase over decades of time. So that kind of ruins out changes in the sun right now to attribute to our current change in climate. The next one on the list, people like to talk about a lot, is, there's variability in the orbit. Our orbit of the Earth changes. Well, got to take each one of these things logically. What do you think changes in the orbit would affect our climate? And if so, how?
Changes in the orbit as far as
So if our orbit changes a lot, is there any reason to think that that could affect our climate?
I'm assuming orbit in relation to the sun. So quite possibly, but I
Right.
don't think I don't think there'd be any consistent change
Okay.
based upon orbit.
So our primary concern with orbit, if we're talking about changes in the orbit, just like Caldrian said, we're talking about distance from the sun, right? And certainly the solar constant can be affected by changes in the distance from the sun. That's the whole point of the solar constant. At our location in the solar system, at our distance from the sun, we have a solar constant of about 1360 watts per meter squared. So we know that the Earth's orbit isn't an exact circle, it's an ellipse. And so we know that there are times when the Earth is further from the sun and sometimes when it's closer. Obviously, this happens every year, right? Because we're going around the sun. This is in part what's due to our seasons. But it's an ellipse, not a circle. And so when you start talking about an ellipse, you have to bring up the term eccentricity. And eccentricity is just a ratio of the height of your ellipse to the width of your ellipse, okay? And what is actually known about the Earth's orbit is our eccentricity changes over time. We call this orbital variability. There are times when our orbit is more eccentric, and there are times when our orbit is less eccentric. And this can be predicted using Einstein's equations of gravity to predict how, over a period of time, the Earth will orbit the sun. Obviously, when it's more eccentric, there will be times when the Earth is at a much greater distance from the sun. And when it's less eccentric, that radius will be smaller and a lower distance. And so you would expect the solar constant to increase. Okay. Now, the problem with using orbital variability to respond to our current climate change problem is that the cycle of going from a very eccentric orbit to low eccentricity takes about 100,000 years. Okay. And we're probably at the far end right now of the more eccentric orbits right now for the Earth. And in about 100,000 years, it will be, closer to a circular orbit. And then 100,000 years after that, it will probably be a more eccentric orbit. So can this really be used to explain our issue with climate change? Remember, we're seeing this sharp change, 1.1 degrees Celsius, over the last 150 years. So is this kind of orbital variability going to be something that that can explain this global temperature rise? Just hoping someone will chime in here and say no, because 100,000 years is, we're not seeing a 1 degree temperature rise in 100,000 years, right? Just not happening. We're seeing it over 150 years. So the change in the Earth's orbit, you really can't attribute to our current change. I've seen so many TikTok videos coming out saying about, oh, all this stuff about fossil fuels is crazy. The Earth changes orbit all the time, and that's true, but that's 100,000 year cycle. Okay. Another one that's popular on the internet is the Earth's tilt. So we know that the Earth is tilted. Okay. Today, our spin axis is tilted about 23.5 degrees from the vertical. Okay. And over the next 41,000 years, the Earth is going to complete a cycle anywhere from 22.3 to 24.5 degrees from the vertical. So our tilt is definitely going to change a little bit. Now, how does this affect our climate? So if you think about the Earth's tilt, we know that we have ice caps on our poles. So if sunlight is shining onto our planet, if the tilt is vertical, less light is going to hit the poles than if less light is hitting, not much light is hitting the poles, that's going to mean our albedo is lowered, which means you would expect warming, right? Smaller albedo means less reflection, means more of the energy is getting to the Earth, so you would get more in heating. Okay. Now, if you increase that tilt, if we've got ice caps on the poles, we would now expect more lights hitting the poles. So we have an increased albedo, it's larger, and so we would expect cooling. And so certainly the Earth's tilt and the fact that the Earth goes through the cycle of tilting will definitely affect our climate, or at least based on the physics that we understand of the planet and how warming is controlled, back to our favorite equation that's got the solar constant and the albedo, we would expect that the Earth's tilt should affect our climate. So do you think that it's the Earth's tilt that's responsible for our 1.1 temperature shift? Why or why not? So Q, you want to chime in here? I haven't heard from you today. Naimungo, you want to throw in your thoughts? Do you think that this tilt could be responsible for that 1.1 temperature change?
No, definitely not. No.
And why is that?
Really just the span of years and the amount of years I'm saying, that wouldn't be able to take place within the 100, the 150 year time period that we have in documenting actual climate change. This is a
Right.
span of course, eons. So no,
Right.
not the one.
41,000 years to cycle between 22.3 and 24.5. So that really can explain a huge temperature jump in just 150 years. Okay. So another one that's brought up is the precession of the equinoxes. Okay. So these are changes in the timing of the closest approach to the sun. Right now, we approach the sun the closest in the month of January. Okay. That's wintertime in the northern hemisphere. And in about 11,500 years, it will actually be closest to the sun in July. So that definitely does change over time. And in 23,000 years, we'll be back to where it is today. So the change in our seasons do change over time. But again, these are over 23,000 years that you take for a full cycle. And so if we look at our orbital variations, we've got our changes in eccentricity, 100,000 year cycles with those. We have changes in our tilt. That cycle takes about 41,000 years. And even changes in the equinox, those cycle every 23,000 years. Each one of these things we would expect to affect the climate in different ways. But because of their timing, they really don't explain any of our modern climate change problems. But they do still, we should still see these effects. And indeed, if you look back into our climate record, remember we saw these ice age cycles. You've seen this graph before. Well, look at the distance in between the peaks. This is from 400,000 years ago. There's 300,000, there's 200,000, there's 100,000. Look at the distance in between these peaks. What do these correspond to? Go back here, every 100,000 years, those
Ice
were our,
ages.
yeah, those were our changes in eccentricity, right? That was changing over every 100,000 years. So there's pretty strong evidence that yes, orbital variability does really affect our climate, because every 100,000 years we see the cycle between an interglacial and an ice age. Remember, our ice ages are these lower periods. The warmer periods are what we call the interglacial, right? So during the ice ages, things are covered in ice and snow, right? And it looks like these interglacial periods fall every 100,000 years, probably due to these changes in eccentricity of the Earth's orbit. Well, if you look at where we are in the cycle right now, what would we expect in the future based on this change? We'd expect temperatures actually to be going down. Now, this is over hundreds of thousands of years, so we wouldn't expect it to go down very fast, but it certainly wouldn't be going up. Now, if you look at these other peaks down here, you notice that there's some other peaks that are occurring. It doesn't just quickly drop off. And that's these peaks over here. And these peaks are occurring about every 23,000 and every 41,000 years. Well, that's interesting because those exactly correspond to the changes in tilt, which cycle every 41,000 years, and the precession of the equinox, which changes every 23,000 years. So all of these peaks are actually explained by these different phenomena that we just talked about that should affect our climate, and they do in the time periods that we would expect. These are called the Milankovitch cycles. It was, I think it's Peter Milankovitch, I'm not sure on his first name, that noted many years ago that changes in the temperature and climate could be mapped to calculations made about the eccentricity in the orbit, changes in the equinox and tilt of the Earth. So all these things are baked in. They're all real effects. So when you see see these things on the internet or people talking about them, they're not lying when they're talking about the actual science behind the effect. They're just not being genuine about the timing, and what it would suggest is happening now. Because in a lot of these cases, it would all suggest we should be getting colder. So orbital variations in all those things are really too slow to explain our current climate change. And so that brings us back to the greenhouse gases. Okay. Now, in chapter 4, we talked about the theoretical reasons why adding CO2 would warm the climate. In chapter 5, we talked about humans are increasing the amount of CO2 in the atmosphere by burning fossil fuels, how that's a difference now in the carbon cycle, something new that's been added to the carbon cycle. We're taking CO2 that's in the rocks and putting it into the atmosphere at a much higher rate than the normal carbon cycle would allow for when you're talking about transport between the atmosphere and the rocks. Okay, generally, the only way you get CO2 from the rocks in the atmosphere is through volcanism and volcanoes, and that happens at about, I think we do 0.1 megaton a year, so it's not a lot, or a gigaton a year. It's a slow process. We're burning fossil fuels much faster than that. Talked about that in chapter 5. And we also have seen graphs that show, a correlation with the geological record of time and with CO2 and temperature. And so I'm just going to give a couple examples that kind of show this correlation. So about 55 million years ago, there was, from what we can tell, there was a huge spike in temperature. We call this the Paleocene-Eocene thermal maximum, or the PETM. Matter of fact, nobody calls it the Paleocene-Eocene thermal maximum. They just call it the PETM because the other thing is just too hard to pronounce. And during that time, we saw between a 4 to 7 degrees Celsius increase in temperature. From what we can tell from the geologic record, there was a massive release of CO2 or methane at that time, and into the atmosphere. And as you would expect, and as we discussed in chapter 5, when you have CO2 in the atmosphere, it dissolves into the ocean and turns into carbonic acid, causing significant acidification. And this acidification in the oceans can dissolve calcium carbonate, which is the material that makes up shells of various creatures that live in the ocean. And so we have geological evidence of this. So here's a graph at about the exact same period of time, shortly thereafter, the amount of calcium carbonate, there's a huge dip in it caused by this acidification because it's been chewed up by the carbonic acid, and that's come right after a temperature shift. And so we know there was a huge increase in temperature. It stayed elevated for about 100,000 years, which is about the time it takes for the carbon cycle to fully remove carbon from the atmosphere, as we talked about in the chapter 5 stuff. And so here we have an example of a huge release of greenhouse gases and then a sudden increase in temperature. And that's consistent with the theory that greenhouse gases drive these temperature changes. And in fact, if you map the carbon dioxide amounts between our ice ages and our interglacials, you'll see they exactly track with our interglacials and ice ages. And here's a really important point that I find really interesting is we already know that these ice ages are initiated by these small variations in the Earth's orbit, right? We've seen that with the periodicity every 100,000 years. That's what gives us these big peaks for these interglacials, right? And then we saw the tilt at every 41,000 years, give us some of these smaller peak in the every 23,000 years for the changes in the equinox. The problem is, though, when you do the calculations in terms of what's the difference in S, in the solar constant, is the changes in sunlight falling on the Earth are actually too small to explain the huge temperature swings that we're seeing during the ice age cycles. Okay, and so that means that something has to be amplifying the effect of the orbital variations to produce these ice ages and these interglacials. And I think you know where we're going with this. And we talked about this in about 2 lectures ago when we talked about carbon cycle feedback loops. Here, it looks like the orbital variations are giving a small initial radiative forcing, causing an increase in CO2. The release of CO2 increases the climate in the familiar way that we're talking about with increasing N, the number of layers should increase warming. This increase in warming now causes a release of more CO2, which then again increases the warming a little bit more, and you get this feedback loop. And really, you can't explain the temperature swings of the ice ages from the solar constant and albedo changes alone. You need something else to amplify it. And since we see that CO2 exactly tracks with this, this provides the amplification that we're talking about that we would need to explain these cycles here. So greenhouse gases seem to have played a role not just now, but also in the changes that we saw with the orbital variations, with the tilt of the planet, and the progression of the equinoxes. I thought that was pretty interesting. What do you all think? Now, is this new stuff or is this stuff you guys already knew? I don't know what they teach out there, you know, how much of, you know, orbital theory you guys cover. But I'm curious to hear what some of your impressions are from all of this.
It's new because it doesn't go as deep in explaining like the precise changes that happen to temperature and how how each particular aspect of temperature is affected by a different by the different highlighted stuff we had. So there is also the so there is also the what do you call? Can you project the highlighted stuff that we ruled out?
Which one did you want to see?
The one that we were canceling out each particular aspect of
Oh,
CO2.
yeah. Okay. Here we go.
Right. So we did do continental drifts, but they were never as deep in relating to the aspect of explaining temperature changes. Then changes in the sun, of course, it wasn't as deep. Then for orbital variability, this is really new. For greenhouse gases, this is, I think this song can be sang by anyone. But it's
Mhm.
really interesting because it builds a strong foundation on debating people who would go for a different approach to what we are going for. So if you and if you factor out all of these things that we looked at, it gives us a stronger convicting point on global warming.
Mm-hmm. Mm-hmm. And one of the things I'm really hoping when you're done with this course, if you run into people who are spouting all sorts of things, you know what the answer is. Like it doesn't catch you off guard and go, well, wait, I didn't know about Milankovitch cycles. What are those? And then you hear about them and you're like, oh, well, maybe that does have something. Well, if you want to talk about every 100,000 years or every 41,000 years, sure, makes a big difference. Um, One of the things that I'd really like you guys to go off to do, and I'm thinking about making an assignment for this next week, is I really want you to go out on the internet and try and find some of the arguments against global warming where people are giving alternate theories. You know, look up alternate theories to global warming or climate change and see what they say. See, are there any arguments out there that sound scientific um, that you don't understand and you can't handle? You're not immediately, oh, well, I know what the truth is on this one. And I'd love for you folks to go out there, look at a few, and tell me, you know, have we covered all of them? Are there a couple that we haven't covered that you don't know how to respond to? Because, you know, by the time you get your master's degree in this, you should be able to, you know, swat these things like flies. So take a deep dive into the internet and see what kind of crazy you can find. Um, you don't have as much a problem with this out in Africa as you do in the US. But we still have a lot of our politicians are still trying, about half of them are trying to say global warming is a crock, mostly because they're heavily funded by folks who are in the oil and gas industry who really don't want us to believe this kind of thing. Um, and so it's interesting to see what kinds of things politicians say. Um, and they try to use a little bit of science. The craftiest ones always use a little bit of truth, like we saw in Senator Ted Cruz. I think I played you a little clip when he was trying to talk about how the satellite record shows that the Earth is cooling. And we talked about going up or going down the up escalator and how if you cherry pick data, you can actually make that argument. But you can refute it by looking at, you know, long range over time. The thing where most of these things fall down is over the time period. A 1.1 degrees Celsius temperature change over 150 years is abnormal. It's unlike anything we've ever encountered before, except maybe that PETM, right? Because there was a huge change there, happened very suddenly. It's hard for us to tell from the record exactly how suddenly that change was, but it does look like a big blip. And you'll always be able to spot the PETM whenever you're looking at historical temperature data or CO2 data or a lot of other data that would have an effect based on if our climate changed suddenly and rapidly. You know, it only lasted about 100,000 years, which is about the amount of time that it takes to get CO2 out of the atmosphere. Another argument for CO2, you know, playing a role. But the 1.1 degree temperature change is just an abnormally short period of time, which really bodes poorly for the rest of our planet because evolution doesn't usually work on that quick of a scale. Things adapt over millions of years and hundreds of thousands of years. not decades. And so we're going to run into some problems, which is why we're in a major extinction event. And hopefully by the end of the course, we will cover a little bit about extinction. Do you guys know much about extinction events? Have you covered that in your former biology classes?
I'm familiar with them, but I've never went in depth with them.
Okay. Do y'all know how many extinction events there have been?
4 or 5, I think.
We're on number 6. We're on number 6.
Okay, yep.
Hold on a second. There's one if I can find it. Let's just see if I can. Probably one of the worst ones. Let's see. Well, I'll see if I can find some interesting stuff on that, because that'll be interesting to talk about, to see how the planet has adapted to sudden changes in the past. And it's kind of sad in some cases, to see just how extreme some of these things have been in the past. Okay, everybody, have a great day. If there's no other questions, I will talk to you on Friday.
Hello, Prof.
Bye-bye. Hi, Shepard.
Yes, Prof. I'm having a challenge with my online class.
With which class?